some ground with respect to deep learning and artificial intelligence. Okay, and we understood about CRISP MLQ framework, in which we understood about business problem, data collection, cleansing the data, machine learning, so on and so forth. And then we have spent significant amount of time on deep learning primer. From deep learning primer standpoint, we understood about human brain. We understood about compositionality. Right? We also understood that within a network, you'll have input layer, and then we also have hidden layers, and you have an output layer. And you'll have an output layer. So input, hidden, and output layer. The number of neurons in the input layer would be equivalent to the number of inputs that we are going to have as part of our database. This is something that we have discussed. We also discussed that initial hidden layers capture low-level features. The next set of hidden layers will capture mid-level features. And the final set of hidden layers capture high-level features. And then you have an output layer. In addition to that, we have neuron. Except for your input layer, all the other layers, hidden layers and output, would contain two components. And those would be integration components and activation components. So you'll have integration components and activation components for all the other neurons, for hidden and output layer. For input layer, you will not have. Here are the various activation functions that we have. Okay. There's of course a lot of literature that we have written here, just for people understanding. But then you have activation functions. You have linear function, which is also called as identity function. Linear function is used when output variable is continuous. Then you also have step functions. Then you have ramp function. You have piecewise linear, which are rectified linear units. Then you have smooth functions, wherein you have soft plus, ELU, so on and so forth. And we also have sigmoid and tangent, hyperbolic tangent. Then you have max out, softmax, so on and so forth. So these are the various activation functions which we have. Then we also understood that when we have a network like this, okay, let me open my profile and let me pull out the specific visualization which we have been frequently looking at. Let me open that. Let me see if I have it in the download section as well. I think I have it. We also have chief. Yeah, I think this makes even more sense. Yeah. So here, if you look at this, if every neuron is connected to every other neuron in the forward layer, this network is called as fully connected network or dense network or multi-layered perceptron or artificial neural network. These are the various names given to this artificial neural network. If every neuron is connected to every other neuron in the forward pass, you get a loss towards the end or a cost. You take that and go back propagate and update the weights. Coming forward, then going back is called as back propagation algorithm, which is used to update the weights. And why are we updating the weights? To minimize our loss function or cost function. And to minimize, we are using optimization techniques. These are the various optimization techniques which exist. There are a lot of additional optimization techniques, but these are a few of those. So that is what is provided here as well. What are the various optimization algorithms that we have, right? And then when it comes to deep learning libraries, there are quite a few, but we will be focusing on TensorFlow and we'll be focusing on Keras. We would, at a high level, look at PyTorch as well. And the last day of the training, we shall have a look at that. Okay. As promised, we need to run the code. Now we need to run the code pertaining to artificial neural network. In order to run the code, artificial neural network code, I am going to resort to Anaconda. When you just go search and open Anaconda, you get an Anaconda prompt. It's coming up. Let it pop up, please. It's coming up soon. Okay. This happens to be Anaconda prompt. We would be executing the code in Spider. We will resort to Spider IDE, Integrated Development Environment, and then we'll execute it here. Let me launch it. Yep, there we go. Sorry, let me pull the code from here. And then we'll load the file and proceed further. No, both are the same, so not an issue. Let me pull the data. Let me put it here. Okay. Even before we get started, one must be aware of deep learning libraries and a few other libraries. Okay, I can do one more thing. If people are not having good computer, you might run into errors. So I shall also, or rather I'll do this. I'll go to Google Collab. Just open Google Collab, the first URL. Let me open a new notebook. It's coming up. So let me rename this as ANN or MN. The code and the datasets would be shared with you all on LinkedIn. Okay. So if you're there on that, you'd get access. Okay. And also here, if you observe, we have an option called connect. Okay. If you go to runtime, you click on change runtime type. In the dropdown, you have GPU, CPU, etc. You can choose if you want to. And I'll click on connect. The moment you click on connect, Google will allocate one available server to you. Then you can execute the code here. So I would copy all the required libraries. And also, even before I execute that, I wish to quickly tell you that here are a few most widely used libraries that one should be aware of. NumPy is used for numerical calculations. SciPy is used for scientific calculations. Pandas is used for data manipulation purpose. Then we have stats models, which is used for statistical analysis. Then we have sklearn or scikit-learn, which is used for machine learning purpose. Then we have matplotlib, which is used for data visualization. You also have Seaborn, which is used for data visualization purpose. Okay, you also have Bouquet, Plotly. All these are the various libraries which are used for data visualization purpose. And then we also have TensorFlow. We have Keras. And then we have PyTorch. When you install TensorFlow, Keras will automatically be installed. Okay, that's how it works. Okay. TensorFlow, Keras, and PyTorch are the deep learning libraries. Go to run it. Let's see what it has to do. Yeah, done. Yeah. So you can say import NumPy as NP. And from TensorFlow.keras, within that you have datasets. Okay. You wish to import MNIST, right? And when you say go to TensorFlow, Keras, in that go to models and import sequential. Okay, so first let me explain this. NumPy contains numerical calculations. So let that be loaded. Now, Keras is an integral part of TensorFlow. Keras is part of TensorFlow. The moment you install TensorFlow, Keras also will be installed. You have a few inbuilt datasets for your practice. Okay, we have a few inbuilt datasets for our practice. And just one. And we are trying to import a dataset called as MNIST. This MNIST dataset contains handwritten digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yeah? These are the handwritten digits. And the moment you have a handwritten digit, say you wrote a PIN number, 500010 in that way. If it is handwritten or otherwise, even if it is printed, you should be able to recognize those. So what you do is each and every number, you give it your neural network algorithm. And neural network algorithm is supposed to classify and tell that this is 5. It should classify and see that this is 0, so on and so forth. Okay, so that's the business problem that we have. Then from TensorFlow Keras models, we are importing sequential. There's something else called as functional. We are taking sequential. Why? Because in sequential, you'll have an input layer, you'll have hidden layers, and finally you will have an output layer. Okay, this is how it works. Then from TensorFlow Keras layers, you're importing something called as a dense layer. You're importing something called as a dropout and flatten. Dense network means every layer would be connected to every other layer. And every neuron would be connected to every other neuron in the forward layer. That is called as fully connected network or dense network. So you're saying, let me take this dense layer. Dropout. You can choose a dropout value. Okay, if you say dropout equal to 0.2, for example, 20% of the neurons in each of the hidden layer would be randomly ignored. We discussed about dropout, drop connect, etc. Then we have a concept of flatten. I would talk about that. Okay, we'll talk about that later. Then there is an inbuilt pre-processing library called as utils. Utils as in utilities. So let me ignore this and let us from Keras itself try to import that. Done. So within Keras, you have utils, you're taking that. Now, if you want to write the next line of code, you can just click on plus sign. But then please remember that comments are extremely important. So before you write a comment, you put a hash and say importing all the required libraries. Right. This is how you proceed further. Okay. Next. Let me now load the dataset. So we will take this dataset and import pandas as PD, and we'll load this dataset. So what we are now doing is we are trying to import pandas also, which is one of the libraries. I think you can put it here itself. Import pandas as PD. So all the libraries that you need for your model building, you're putting that in a specific location. And this is called as code modularity. It is extremely important to maintain code modularity. because the moment we maintain code modularity aspects, the code that you write would be very meaningful. Even readability aspects will increase actually. Then within this library called pandas, pandas is used for data manipulation purpose, such as loading the data and so on and so forth. And here you're saying pd pandas dot read underscore CSV. This is a function using which you read a CSV file. But where is that file located? You need to put that in Google here. So here, do you see the small file icon? Click on that. And you can load it here. Right click, click on upload. Then here, sorry, let me go to FTP. Here we have the training data and test data. I'm loading both of those. Once you close the session, those files will be gone. So those two files, if you see here at the bottom, are getting loaded onto our Google Drive, or only for this instance. So you have the training sample. You see those three dots, click on that, copy the path, and just paste the path here. So that's the path where we have the file. Okay. Now for test sample also, I'll just do a drop down, copy the path, and I paste the path here. And now let me click on run. So what we are doing is we are using pandas. You are using a function called as read underscore CSV. And within the brackets and double quotes, you're giving the complete path along with the extension. And using assignment operator, you're assigning it to an object called train. Here, using an assignment operator, you're assigning it to an object called test. So you have train and test. Then I just hover, I get new code. Then we need to do pre-processing, data pre-processing. For data pre-processing, we have a bunch of these. So let me first load them. Okay. Before that, again, as I've told you, you need to write the comments. What are we doing here? We are loading the data sets. Okay, because once you have the data set, you can process it. So what are we doing here? We are separating the data set into two parts. All of the inputs will be one part and label will be another part. And here, what we are trying to do is we are trying to convert integer type into float. Why? Might be a question. Let me answer at this point of time. So if you have a network, you'll have inputs, you'll have the hidden layer, and you'll have the output layer. And you'll have all these connections. Okay, you'll have all the connections. And then you'll have the output. Okay. We know for a fact that the weights are randomly initialized. So you'll have weights, W1, W2, W3, in that way. All the weights would be there. Here also you'll have weights. I'm not including bias, mind you. You'll have bias here also, here also. And the bias will be connected to all the neurons. Bias will always have an input 1. Bias also will have a weight called as B, which are randomly initialized. Here also you'll have some weight. So all these weights are float values. All these weights would be float values. Float means decimal values. So these weights are randomly initialized. You'll have no control on those. They will be in decimal, randomly assigned, so they can also have decimal values. You will have no control on that. However, if you have your inputs, which are in integer format, integer means non-decimals. What do you mean by that? Suppose you have a digit 1. Okay, assume you have a digit 1. This 1 would have a lot of pixels. This is an image, handwritten digit 1. This is an image. Each pixel value in the image will have some pixel intensity value. You'll have some pixel intensity value. This pixel intensity value ranges from 0 to 255. 0 means black color. 255 means white color. Okay. 0 means black color. 255 means white color. So these pixel intensity values are integers. They don't have any decimal values. Either you'll have 0 or 1 or 2 or 3 or 4. They're integer values. So your inputs will be integers, but your weights are float. If you multiply integers and float, you get an error. To avoid that error, we are converting the inputs into float format, because this is the only thing that you can control. Weights you cannot control. You cannot say that let me convert weights into integer. That option doesn't exist because your algorithm itself is built in such a way that the weights are randomly assigned. So given this context, you convert inputs into integers. So that, you convert inputs which are integers into float value, so that float and float, when you multiply, you don't get any error. So what we are doing here is, as a line of comment says, we are separating the data set into two parts. All the inputs you want to put it in one, and all the output you want to put it in another object. So what you're saying is, let me go to this training data set. Let me go to the index location. And whenever you see these square brackets, it's always rows, comma, columns. So colon means you want all the rows. One colon means you want the columns from 1 until n. Okay, you want the columns from 1 until n. And you're saying, let me take all those values and let me convert that as type. Float 32. 32 means 32-bit machine computer. 64 means 64-bit computer. So you'll have 32-bit as well as 64-bit. Okay, you have 32-bit and 64-bit computers. When you say float 32, your values, which are integers, are converted into float, which are decimals. Integers means you won't have any decimals. Float means you'll have decimals. Float 32. Then, or 64. If you have a 32-bit computer, 30 to 64 are the latest of the computers. You can put 64. To be safe, you can put 32 because it's compatible on both older machines and newer machines, older computers and newer computers. And then we are assigning it back to x_train. We are creating a new object. That's on the input pertaining to training data. So you're taking the test data now, index location, take all the rows and columns from 1 until n. You take all the values corresponding to that and convert them into float and assign it back. Then go to the training data, take the label. Label means your output variable. And take all the values in that output variable, convert that into type float. This part wherein you're using as type is called as typecasting. Typecasting or coercion. Coercion means, or typecasting means converting one type to another. Okay, forcibly converting one type to another is called as typecasting. Okay. So you do that on all inputs and outputs. Job done. Next. This is one pre-processing step that we have done. Next, we know that when you have, say, if you have a handwritten digit 5, for example, this particular handwritten digit or image will have a lot of pixels. And each pixel value will contain pixel intensity. And these pixel intensity values range from 0 to 255. 0 means black color and 255 means white color, right? So these are the pixel intensity values. Okay, then if you have 255, it's a very big number. If you have a pixel value 0, it's a very small number. When you have these kind of values in your data set, you run into an issue called as scaling issue. Okay, you get into a problem called a scaling problem. To fix the scaling problem, you can apply scaling technique. And one such normalizing technique here is you divide each and every pixel value with 255, with the highest value. If you divide 0 with 255, you get 0. If you divide 255 with 255, you get 1. So the new values will lie in the range of 0 to 1. So from a larger scale, there's a huge difference, 0 and 255. Right? You reduced it to 0 to 1. If you normalize it in this way, your algorithm will run faster. Okay, that is what we do. So we are by dividing the entire data with 255. This is what you do. Next, here the output variable is 0 or 1 or 2 or 3 or 4 or a 5 or a 6 or a 7 or 8 or 9. Handwritten digits. How much ever bigger the number is, only these digits will be there in that. 0 until 9. And when your output variable is categorical, and if you have more than 2 classes, here you have how many classes? 10 classes. So it's a 10 class classification problem. Okay, so we have a 10 class classification problem that we are trying to solve. All right, next. If we have a 10 class classification or multi-class classification problem, there are a couple of things that we need to remember. That is, in the output layer, okay, in the output layer, you will have 10 neurons. Point number 1. Because it's a 10 class classification problem. So in the output layer, you'll have 10 neurons. This is first point. Second point to remember is that when it comes to loss function or cost function, you have to use categorical cross entropy. And the third point that we need to remember is that the activation function, okay, activation function in the output layer should be equivalent to, the activation function that you have to use is softmax. These are a few things that you need to remember, given that the output variable is categorical. So if your output variable is categorical, in the output layer, you're going to have 10 neurons. The loss or cost function to be used is categorical cross entropy, and the activation function that we are going to use is called as softmax. Okay. In order to calculate this categorical cross entropy, your output variable that you have should be converted into one hot encoded format. You might ask me, why is that so? Okay, let me explain. Hold on. So if you want to calculate cross entropy, the formula for cross entropy happens to be summation of I equal to 1 until n minus pi into log of qi base 2. And you have 10 classes. What are those 10 classes? 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is a 10 class problem. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you have a new digit and that happens to be digit 4, for example, so what will you have in your actual data? Actual data, let me call it as P. So it's not 0, this is not 1, this is not 2, this is not 3, but this is 4. So against 4, you'll have 1. Rest all these values. And then you have the predicted values. You have predicted values as Q. For predicted values, you'll have some probabilities. 0.01 probability that it's 0. Okay, 0.08 probability that it's 1. In that way, you'll have some probabilities. And obviously, there will be very high probability for 4. Rest all, you'll have some number, 0.06, 0.04. Okay. In that way, let me call it a 0.2. Then that 0.02, 0.03, 0.03, 0.02. Okay, in that way, 0.01. In that way, you'll have some probabilities. Now, if you want to calculate cross entropy, you'll say that it's a 10 class problem minus I equal to 1 to 10 pi into log of qi base 2. Then when you substitute I equal to 1, you get minus sign will be there. P1 into log of q1 base 2 minus is this one. When you substitute I equal to 2, P2 into log of q2 base 2, I equal to 3, P3 into log of q3 base 2, so on and so forth. Until 10 classes. So it will be P10 into log of Q10 base 2. Now just substitute all these values. This is P1, this is Q1, P2, Q2, P3, Q3, P4, Q4, so on and so forth. Substitute in this equation and you get some number, right? That's called as loss or cost, which is cross entropy. And since you have multiple classes like 0, 1, 2, 3, it's called as categorical cross entropy. To calculate this, your actual data that you have should be in this format only. It should be in one hot encoded format. This is called as one hot encoding because only one of these will have one, rest all will be zeros. So against 4, you're having one, rest all zeros. So this is called as one hot encoding. Okay. So to convert your data into one hot encoding, you use this function, which is an inbuilt function. Someone else has written the code. And when you use this function, automatically it will convert all these into different values. Okay. So to categorical, output you're converting into categorical. To categorical means it does one hot encoding. You're doing that on the test data as well. Once you're done with this, when you say y underscore test dot shape, you'll understand how many rows are there and how many columns are there. And if you look at this data, if you have a 10 class problem, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then how many columns will we have? 10 columns. When you say dot shape, you'll get rows by columns. Rows will have an index number 0 and columns will have an index number 1. When you say go to this test data of 1, you're referring to the number of columns. If you have 10, the number of, columns also will be 10. And you're saying that is nothing but number of classes. Yes, you have a 10 class problem. if you have 10 classes and when you do one hot encoding, you'll have 10 columns. So number of columns is equal to number of classes. So you're just taking number of columns and you're putting that in number of classes, which is 10. Then if you do all of these, you get to see what is the shape of the data. Usually if I run this, right, only you will see the last code output. If you want the output for all of these, for example, say you want to look at how many classes do I have, right? Then before that, you just need to insert print. Here also, if you want this output also, then just insert print. Here also you can insert print. Here also you insert a print. And then here also say print. Now if I were to run this, you will see the output for all of these. So if you observe, you have 2,865 rows. And how many columns do we have? 784 columns. Because in this data set called as MS dataset, which has handwritten digits, that is the images. It's 28 by 28. Each image, say you have 5, is of size 28 by 28. Means you'll have 28 rows and 28 columns. 28 by 28, if you multiply, you get 784. So the data set will look like this. So if this digit is 5, if that's the output variable, how many inputs will you have? 784 inputs. Each of those will have the pixel values. Okay. And the training data output should have had 10 here. Why are we having 6? Let me rerun it and see. Is there something wrong with the underlying data itself? I don't know. Let me try out once. Oh, yeah. Sorry, my bad. I think the processing did not happen properly. By the time we loaded, right, I think entire data was not loaded. My bad. So here now what's happening is in your training data, you have 1 until 5,000 rows and you have 784 columns, X1, X2, X3, all of that. So that's your training data inputs. What about the training data outputs? It's stored separately, but then the output also has 5,000 rows and 10 different columns. So same 5,000 rows, but it will have 10 different columns. Why 10 different columns? Because it's a 10 class problem. You have done one hot encoding, 0, 1, 2, 3, all the way until 9. If the first digit happens to be 5 as an example, so you will have 0, 0, 0, 0, 0. Against 5, you'll have 1, rest all zeros. Then when it comes to the test data, you have 1,000 observations and you have 784 columns. And when you look at the test data output variable, you have 1,000 rows and 10 columns. Okay, that's how we have. All right. So let me add the next column, sorry, next cell. And we will design our activation function. We will design a network. Let me do it. So we are creating a user-defined function. User-defined means you are writing the function. If you directly use functions like this, it's called as using inbuilt functions. When it comes to functions, my dear friends, which are part of obviously, okay, you will have inbuilt functions. Inbuilt functions are part of libraries. And you also have custom functions or user-defined functions. Why is it called as user-defined? Because it's not there as part of any library. You need to write it on your own. And that's what we are doing. And this is the syntax or format in which you write a function. What are we trying to do here? This is the syntax or the format in which you write. DEF space, you give a name to the function. You can give any name of your choice, but let it be logical. What are we doing here? We are saying it's a design for MLP, multi-layered perceptron. Open and close the brackets, colon, and click on enter. The moment you click on enter, you'll have an indentation. Indentation. So indentation is created. In this indentation, you're writing a hash and you're writing the name, initializing the model. And first of all, we are trying to have, we are defining an empty sequential model. And you're storing it in an object called model. Empty, nothing is there. And what you're doing then is you're adding layers. How are you adding layers? You're saying the input dimension. So the input layer should have how many neurons? 784 neurons. These 784 neurons, you're then connecting it to 150 neurons. 150 neurons are there. You're connecting to them. And you're saying it should be dense. Dense means every neuron should be connected to every other neuron. Okay. Then you're saying that the activation function should be ReLU. So within these, you need to have ReLU activation functions. So I draw it that way. You have integration, activation, integration, activation, integration, activation. And ReLU is a activation function that we have. That you're connecting to the next layer, which is also dense, wherein you have 200 neurons. So you have 200 neurons in the next layer. Once you say dense, every neuron will be connected to every other neuron. And here you're using an activation function called tanh. So every neuron will have integration component and activation component. Activation is tanh. Then you're connecting that to next layer where you have 100 neurons. And again, you're saying it should be dense. Dense means every neuron will be connected to every other neuron. And then you're saying within these, let's use tanh activation function. Again, that you're connecting to another layer wherein you have 500 neurons. Now, if you ask me a question on how many such hidden layers should I have and how many neurons should I have within each hidden layer, there is no rule. There is no rule. You can have as many neurons as possible. Okay, there is no condition or rule as such. And you're using tanh activation function. Then the output layer should have, how many neurons should we have in the output layer? 10. Why 10? Because it's a 10 class problem. And in number of classes, you have 10. So you'll have 10 neurons. And in the output layer, you need to have softmax activation function. This is also something that we have discussed. Dense means every neuron is connected to every other neuron. This is called as designing your model. This is called as a design phase. You're designing your neural network. And once you design your neural network, what is the next step? You compile your model. When you compile your model, you need to give the loss function, optimizer, and metric. Three things we need to define. Loss is categorical cross entropy because the output variable is multi-class. Optimizer, there are a bunch of optimizers. Choose anything of your choice. And metric, you're saying I want to measure the accuracy of the model. Okay. So here you're compiling the model. You design, compile, and run the model. This is compile phase, in which you will give these three details. Then you say return the model, means once you run the model, you give that as an output, is what you're saying. This is the function that we are designing. Done. The design part is done. What do we do next is something that we will talk. It is almost 3:05. So let's take a break at this point of time and come back. It's almost 3:04. So we will be back in 15 minutes, 3:20. Yeah. Let's be back at 3:20, friends, and we will take it forward. Thank you. Okay, so I think we can get started. So we have defined or designed the network, right? So what are the various things that we have done? We have imported the required libraries. We have loaded the dataset. We are separating the dataset into two parts, inputs and output. Then we have done data pre-processing. And then we have designed the network and compiled the network. Now we need to take it to the next level. So I click on forward. We have new block which got created. Let me fit the model. How are we fitting the model? We're just taking this function and storing it in another object called as model, another object. And then we are saying, let us fit the model. When we say fitting model on training data, you provide your training data inputs, training data output. And you need to provide batch size, number of epochs, and what is the validation data on which you want your model to be validated. So when you have your data, you split that data, right, into training, validation, and test, if you remember. That's what we have done. And then you build your model on this data, training data, test it on the validation data. Okay, so here, when you say model.fit, and the moment we give batch size equal to 1000, what does that mean? That means that it's a mini batch stochastic gradient descent that you want to run. And if you observe this complete data, you have 20 epochs. Epoch 1 of 20, 2 of 20, in that way you have 20 epochs. And in your training data, we already know that we have 5,000 observations. If you look at this training data, you have 5,000 observations. Output also has 5,000 observations, rows. Since you have 5,000 observations, and if batch size is 1,000, if I say we have overall 5,000 observations, and if I say batch size is 1,000, how many batches will we have? 5 batches. So 1 until 5,000 is divided into 5 batches. 1 to 1,000 observations is batch 1. Then 1,001 until 2,000, you have the second batch. This is batch 2. Then 2,001 until 3,000, you have a third batch. Then 3,001 until 4,000, you have the batch 4 or the fourth batch. Then from 4,001 until 5,000, you have fifth batch. These are the 5 batches that we have. Okay, then. You have 3 seconds, 56 milliseconds. I mean, that's the amount of time which has taken to complete the first epoch, which has 5 batches. So 5 out of 5 batches to train, it has taken 3 seconds, 56 milliseconds. Loss is given, okay, accuracy This loss and accuracy are pertaining to your training data. And then this validation loss and validation accuracy is part of this validation data. The test data, you're calling it as validation and putting it here. It's simply put test data if you want to call it that way. So you'll have your inputs and you'll have your output. Then you'll have the loss. Okay. That loss will be something like this. Then as part of next epoch, 5 out of 5 batches. After end of each batch, your weights get updated. So 5 times your weights get updated actually in one epoch. It took 10 milliseconds and the loss value reduced from 0.95 to 1.09. And accuracy increased. Obviously, when loss decreases, accuracy will increase. Same is happening with validation loss also. That also decreased and hence accuracy is increasing. Then epoch after epoch, epoch after epoch, when you're done with 20 epochs, your loss has reduced significantly to 0.0249. Accuracy has increased. This is training loss and training accuracy. And the validation loss and validation accuracy happens to be so much. Ultimately, we are expected to compare the training accuracy and validation accuracy. And if both these accuracies are high and close to each other, it is called as right fit. If the training accuracy is high and validation accuracy is low, then you call this scenario as overfit scenario. Overfit is also called as variance. When you have overfit or variance, you address that issue. You need to address using regularization techniques. A third scenario is when your training accuracy is low, and when you're, in that case, your validation accuracy also will be low. This scenario is called as underfit or bias. In either cases, you resort to regularization techniques, and regularization techniques will help you fix the issues. Okay, and let me get to this GIF and let me show you that. If you all remember carefully, these are the various regularization techniques which we have. Early stopping, dropout, drop connect, adding. You apply these regularization techniques to ensure that you have variance bias trade-off. Meaning overfitting, underfitting trade-off. Also, we have in this, we have solved this use case wherein we have output variable which is categorical and more than two categories. Okay, when you have more than two categories, as part of your loss function or cost function in your output layer, you use categorical cross entropy, point number one. Okay. And also, when it comes to the output layer, you have n classes, and we're using softmax activation function. Activation function being used as softmax. All right. So this is what you will have to be aware of. So whenever you have data, you need to pre-process the data, build the model. Okay, we build the model, and there are a lot of hyperparameters. Like when it comes to our neural network algorithms, what are the various things that can be experimented with? Number of hidden layers, which is a hyperparameter. Number of neurons in the hidden layers, right? Then optimization techniques. Then what should be the activation function, right? What should be the loss function or cost function? What should be the batch size? What should be the learning rate value? All these are hyperparameters within neural networks. And this is a scenario that we have dealt with. What next? Of course, by just looking at the last epoch, accuracy and validation accuracy, you can figure out whether your model is a right fit or not. Finally, you need not even evaluate, but that's okay. Say you're evaluating. The model that you built, when you say dot evaluate on the training data, and when you say verbose equal to 0, it doesn't give you any output on the screen. Okay. And when you run it, you get some accuracy. And you're saying that that accuracy, you want the values in percentage, and you want 3 floating point values. After dot, you want 3 digits. And then you're saying in that percentage, you want to have score, because you're, after building the model, you're storing the results in this. Okay, and let me print that and then show you. Maybe then it makes sense. So what are we doing? We are saying model.evaluate on training inputs and output, and verbose equal to 0. And then you're storing the results in this. And then when you print the results, these two you get. Right? When I say verbose equal to 1, you get certain additional details on how much time it has taken, right? Loss accuracy. If I say verbose equal to 2, you get slightly more information, right? How many observations it has actually run on, what is accuracy, how many seconds it's taking for each epoch, for each step, how many seconds did it take, and additional details, right? If I say verbose equal to 0, it doesn't give you anything. It will just give you loss and accuracy. Now this loss here will have an index number 0. Accuracy will have an index number 1. Hence, when you say of 1, it will refer to this, and you're multiplying this value with 100. And when you do that, you're getting an accuracy of 99.86%. Okay. So using the model that was built, when you now test when you now test on the training data, you get an accuracy of 99.86. Then here also we are doing the same thing. Let me print eval underscore score underscore test. When you run this, you get the loss and accuracy. Loss will have an index number 0, accuracy will have an index number 1. Then when you print the results, so accidentally that 4 appeared. Your of 1, this of 1 would refer to this. If you multiply it with 100, you get this value, 94.9%. And why do you have 3 digits? Because it's a 3-point floating value. It's not just about building the model. Once you build this model, you will also have to deploy this model in production. Right? So we build the model, accuracies are high and close to each other, right? 99.8, 94.9. They're more or less close to each other. So you can conclude that you have just built a right fit model. But then, if I were to go to the mind map, I'll select this certificate program, or I would select practical data science in AI, because it's crisp MLQ framework now. And you have phase 1, 2, 3, 4, 5, and 6. So until 4, we have completed. Now we need to get into 5 and 6. 5 is model deployment. That is, where are you going to deploy your model? Okay, that's very important. Where are we going to deploy? So deployment part, I'm not going to explain today. We will do that in the next module. But in this module, we would switch our gates now to CNN and talk further about this theory. And then tomorrow when we connect, we will take this to a logical closure. Monitoring and maintenance is something which happens on an ongoing basis. You build your model, you're happy with the accuracy, it's a right fit model, you deployed the model. When people start using the model, you will start capturing the details, the monitoring and maintenance details you'll be capturing. So let me tell you that if you have structured data, which is tabular or columnar data. If you have tabular or columnar data, then you proceed further with multi-layered perceptron or artificial neural network or dense network. And if you have unstructured data, such as videos or images, we proceed further with convolution neural networks, CNN. If you have textual data, which is an unstructured format, we proceed further with something called as RNN, recurrent neural network. So let's understand this component. And I should also tell you that if you have videos are nothing but combination of multiple frames of images. So you have multiple frames of images. That is what videos are made up of. Within a video, you'll have image. Okay. This frame is nothing but one image. And this image will contain what? Pixels. That's a raw feature. The most basic feature is pixel intensity values. Okay. This is about your unstructured data. Okay. Next. Let's proceed further with convolution neural network, and discuss the theory before we proceed further. So welcome to the world of images. Okay, just a moment while I try to. You have to just allow me a quick minute. I'm fixing something here. All right, welcome. So when it comes to images, dealing with images, I mean, dealing with videos is nothing but dealing with images only, because ultimately, when you have video, you're going to split the video into images. Okay, video would be split into images. And computer vision applications, image processing applications, etc. For these, majorly people use OpenCV and the Python version of OpenCV, Open Computer Vision, which is an open source library. Many people use that. The neural networks in the space of videos or images became very famous thanks to the ImageNet competition. In the original dataset of ImageNet, there are 14 million images, and people have hand annotated by looking at the image, they've given name to the images. Very tedious task. And there were 22,000 different categories. 22,000 different categories, like trees, one category, flower is one category, right? In that way, 22,000 categories. But for this competition, which they have announced, they've given 1.4 million images for people to work, and there were 1,000 categories. 1,000 categories and 1.4 million images. And then people were expected to build a model which would give an accuracy, or which would give highest accuracy possible, right? So that's the idea. So let's proceed further. So in this competition, 1.4 million images, and there were 1,000 classes. Just give me one quick minute, sorry. One quick. Hey, sorry everyone for that slight delay. Okay. This competition, ImageNet competition, was called as ImageNet Large Scale Visual Recognition Challenge. Now they stopped it because it's a solved problem, meaning the goal of artificial intelligence is achieved when it comes to image detection. No, sorry, or classification rather, let me put it that way. Because the moment there is an image, automatically your algorithm will classify it. And that's the kind of accuracy that we have achieved now. Okay. And from year 2012 onwards, in the year 2012, Alex Krzyzewski has come up with an algorithm, which was a winning architecture. The architecture, number of neurons, etc., was amazing. And from there on, every neural network architecture that people have experienced was related to, or all the award-winning architectures were related to neural network. You can recognize images. Of course, there are a lot of challenges, but a lot of those challenges are fixed now as we stand. There is this compositionality aspect that we have spoken about when it comes to image. First, pixels are learned, then edges, then text on, then motif, then parts, then objects in that way. You have image classification problem. Classification means tell me whether it is a cat or a dog. Classification. Detection means if you have a cat and a dog in an image, it will detect and say this is a cat, and it will detect and say this is a dog. It will detect those objects. Whereas given an image, if you want to just classify, you can do that. There is also image segmentation, wherein if you give an image as an input, all the people, if you see, are color coded differently. The road is color coded differently. The trees and plants are color coded differently. In that way, every different object is given a different color code. Then when you have a driverless car going on the road, driverless car should detect what are the objects. And using sensors, you determine what is the speed at which they're traveling. What is the speed at which you're traveling? Will they collide? Okay, will the vehicle collide into those vehicles? We don't know. We need to track that. Also, people are doing predictions on whether those vehicles will come in front of these vehicles or not. That's also another thing. And then not just that, your driverless car should also understand those signages. Different signs are there, right? It has to figure out those signages. Because if it's 70, you cannot cross 70 miles per hour or kilometers per hour. Okay, so on and so forth. And then you also have pose estimation. Pose estimation are different things that one should be aware of. Then you have convolution networks, for facial recognition, for pose estimation, for numbers recognition, to detect how many veils we have, to overlay a map on top of your map, and giving names to the images. So that's called as image captioning. You have multiple images. You give a caption to each and every image. Okay, like a person riding a motorcycle on a dirt road, right? The moment you look at this image, you get this caption through your convolution network. Now the question is, when we already have multi-layered perceptron or artificial neural network, which is also called as dense network, or which is also called as fully connected network. When we have this in place, why do we need convolution neural network. Already you have a neural network architecture here. Why can't we use the same? Why do we need altogether a different architecture? This is what we need to talk about. Suppose, just for our clarification and understanding, you have a dataset called as Cipher dataset. In the Cipher dataset, say you have images. And say you have images of size 32 by 32 by 3. So each and every image has a width of 32 and height of 32. And say there are 3 color channels. What are those 3 color channels? Red, green, and blue. In a color image, those 3 channels will be there. Then, do you know what? In your neural network, the number of neurons, rather than draw those many neurons, I'm just drawing a line, you'll have 32 by 32 by 3. These many neurons will be there. Even if you have one hidden layer, this 32 by 32 by 3, you multiply it with 3. And 32 by 32 is considered to be a very small image. Very, very small image. Usually you have what? 10 megapixel camera, etc. 10 megapixel means 10 into 1 megapixel is 10 raised to the power 6. So if you have a 10 megapixel camera and if you have such a high quality image, do you know what will happen? You will have 0, 0, 0, 0, 0, 0. Okay, and 1, 0, 0, 0, 0, 0, 0, 0. These many pixels will be there. These many pixels you're going to have. Into, if it's a color image, multiplied by 3. Oh my God. The number of weights that your model has to learn would simply explode. It's like 10 raised to the power 7 into 10 raised to the power 7 into 3. Huge number of neurons will be there. And when you connect every neuron to every neuron in the forward layer, these many weights your model has to learn. So your number of weights will just simply blow out of proportion. It will explode. So what should I do then? So people thought, first challenge is that the number of weights or number of parameters would be insanely large. Number of parameters would be extremely large. Okay, this is one part of it. Second thing is, if this is an image, and if you have a human face here, okay, suppose you have a human face here. To recognize a human, you just need to have this portion, which is that local region. This is called as local, this local region. But what are you doing as part of this? You're taking every pixel. Every pixel is considered. So it's called as a wastage, right, of unnecessary resources. When you want this patch, why do you want all those other things? Okay. So here, the full connectivity of neurons is wasteful in the framework of image recognition. And the huge number of parameters quickly leads to overfitting. Wasteful of all those neurons. Why do you need those many, right? So two challenges. One is the number of weights explode, and another is the full connectivity of neurons is wasteful. So like this, if there is an image, you connect all the neurons to all the neurons in your hidden layer. That's even more wasteful. So the spatial correlation is actually global if you take everything. It's wasteful of resources. Hence, people thought we need a different architecture to deal with images. And that gave rise to one of the world-class algorithms called as convolution neural network. And convolution is an operation which you perform on an image. Suppose you have an image of size 5 by 5. Okay. And suppose you have a filter, or you can think about this as a hidden layer. Okay, suppose you have a hidden layer. Hidden layers in convolution neural network are called as convolution layers. Okay, in that convolution layer, say you're having, this is called as a filter or kernel or a mask. Filter or kernel or mask all mean the same. And in this filter or kernel or mask, you have, say you're taking 3 by 3. You can take any size, 3 by 3, 4 by 4. Of course, it should not be more than the size of your image. So you have your image, you have your filter. When I apply this filter, that application is called as convolution. When you convolve this filter on this image, obviously you apply this on this patch first. On this patch. When you apply on this patch, and the values here in this filter would be automatically generated. Those are nothing but weights. In your neural network, you'll have weights, all these weights, which are randomly initialized. Those weights are nothing but the filter values. Okay, the filter values are weights. So you take all the values. Say your weights are randomly initialized as 1, 0, 1, 0, 1, 0, 1, 0, 1. Randomly, some weights are initialized. When you apply those filter on this patch, you say 1 into 1 plus 1 into 1, 1 into 1 plus 1 into 0. These numbers that you have on your image in black color are your pixel intensity values of the image. Yes. 1 into 1 plus 0 into 0 plus 1 into 1 plus 1 into 0 plus 0 into 1 plus 0 into 0, 1 into 1. When you do this multiplication and solve it, you get 4. And that is what is given here. So when you apply on this patch, right, what would you get? You'll get this central pixel value. You're just making use of your neighboring pixels, but ultimately you get the central pixel value as 4. Then what happens? This will move on. And oops. This patch will move to the next patch. And when I say stride equal to 1, then let's see how it moves in this way. So what's happening? This patch that you have, or this filter, is convolving on the next patch, and you're moving it by 1 pixel. Why is stride equal to 1? Then do the same thing, 1 into 1 plus 1 into 0 plus 0 into 1 plus 1 into 0 plus 1 into 1, so on and so forth. Add them up. And then once again, you get the central pixel value. And the central pixel value is nothing but 3. Then again, you move this stride equal to 1 by 1 patch. Again, 1 into 1 plus 0 into 0 plus 0 into 1, so on and so forth. Do that. And once again, you get the central pixel value, which happens to be 4. Then keep moving it. Again, 1 stride. 1 stride means 1 pixel. Again, when you do this calculation, 0 into 1, 1 into 0, all that, you get the central pixel value, which happens to be 2. Then stride equal to 1. Again, move it, move it, move it, move it until your complete image is processed. You keep moving it. Okay, and you get these values. This is your output. So what is your input? Your input is an image. You're applying a filter or a kernel or mask on that. You're convolving it rather. And when you convolve it, what are you getting ultimately? The output, which is called as convolved feature. Okay, next. This is the output that you get. So now let's look at, did it address the issue that we had in multi-layered perceptron? That the number of weights were too many. And here what will happen is, if you have an image of size 5 by 5, you'll have 5 by 5, which is 25 neurons. And if you have a filter of size 3 by 3, so you'll have 3 by 3. 3 by 3 means 9. Then, if you want this output, so what ultimately happens is this. When you apply it on this patch, for instance, and say this filter, the filter values of this happen to be 1, 0, 1, 0, 1, 0, 1, 0, 1. So the weights, same filter values will get applied on every patch. If you apply on this patch, you get the central pixel. Okay, and that happens to be 4. But anyways, what are we doing? You're applying on these 3. 1, 2, 3. So what are the weights? 1, 0, 1. 1, 0, 1. These 2 you're not applying on these 2 because the patch is only so much. Then on this also you apply. Here also the filter is getting applied. And what are the weights there? 0, 1, 0. So you have 0, 1, 0. Then on this also you're applying 1, 0, 1. You have 1, 0. So you have these weights. Now, when I apply this, so this is what I'm saying. This is the patch on which you're applying. Correct? This is a patch on which we are applying. And you get this central pixel value, which is this. If you apply on a different patch, say you're applying it on this patch, or let me say this patch. So what would happen is, okay, sorry. And if you apply on this patch, the same weights are getting applied if you observe. And you want this value, right? This. So here what's happening is the weights remain the same. 1, 0, 1. Then 0, 1, 0. Then 1, 0, 1. On any patch you apply, the weights will remain the same. So overall, how many weights your model will learn? Only 9 weights. So in comparison to multi-layered perceptron, the number of weights have significantly come down. Okay, the number of weights have significantly come down in comparison to the multi-layered perceptron. Okay. So that problem is gone. And also, are we connecting every pixel in input to every neuron? Every neuron in input, are we connecting to every neuron in the hidden layer? No. We are only connecting a few here, a few here. So you're not wasting the resources. So both the issues of multi-layered perceptron are addressed in convolution neural network. Now let's understand the neural network architecture in a further detail. So we have a convolution layer wherein you have an image of 32 by 32 by 3. So height is 32, width is 32, and depth is 3. Usually when we say depth equal to 3, that means it's a color image. Depth equal to 1 means it's a grayscale image or black and white image. And whenever you have a filter, that filter will consume the entire depth of the image. So say you have a filter of size 5 by 5 by 3, that would, even if you say I want to apply a filter of size 5 by 5, it will automatically take 3. So the depth value will automatically appear here. So the filters will always consume the entire depth. And after that convolution, you get an output, which is called as activation map, which is nothing but some features from your image are extracted. Some features from your image are extracted. It's called as black box algorithm. The deep learning neural network is called as black box for this reason. It is also called as a response map or representation map. So some representations, some response, some activation is what you get. It's of size 28 by 28 by 1. How did we get 28 by 28? Might be a question. So if you have an image of size 32 by 32, and if you're applying a filter, why did I get 28 by 28? For this, Let me first explain using small example, this example. If you have a filter of size 3 by 3, and if you're applying this filter on an image which is of size 5 by 5, what happens, right? Let's understand. If you apply this on this patch, fine, you get the central pixel value, which happens to be 4. Someone is scribbling on the screen. Okay. But then, if I want this value, this pixel value, then I need to apply this filter on this patch. But I cannot apply because these pixel values are missing. Since these pixel values are missing, you cannot apply on this patch. These pixel values are not there in your input image. It's only 5 by 5. So on the border pixels, you cannot apply your filter. Hence, all these border pixel values, you cannot get it. Because in order to get this pixel value, for example, here, it's 3 by 3, right? You should have applied it like this. You should have applied it like this. But applying it like this means you need pixels here, but we don't have pixels. Right? Since you don't have pixels, there is the story. Okay, so you cannot get these border pixels. Hence, when you have a 5 by 5 image, and when you apply a 3 by 3 filter, you get an output which is of size 3 by 3. How? Right? Let me say size of the image is n by n, 5 by 5 in this case, n by n. And the filter, let me call it as f by f. And the formula to get the output is n minus f divided by stride plus 1. What is n value here? 5 by 5. Minus filter value is 3. Divided by stride is 1. You move 1 pixel at a time, right? Stride equal to 1. Plus 1. So 5 minus 3 is 2. So you get 2 plus 1, which is 3. So the output dimension is 3 by 3. And on similar lines, when you apply a 5 by 5 filter on 32 by 32 image, it's n minus f divided by stride plus 1. N is 32. Filter is 5. Divided by stride is 1 plus 1. So you get 27 plus 1, which is 28. So you get a final image of size 28 by 28. If you apply one more filter, I mean, you can apply multiple filters. If you apply one more, you get one more activation map of size 28 by 28 by 1. If you apply in that way, say you're trying to apply 6 filters. If you apply 6 filters, you get 6 different activation maps. 1, 2, 3, 4, 5, 6. You get 6 different activation maps. This is how it works. Okay. Now, If you apply a 5 by 5 filter, automatically it will take 3 because the depth is 3. And if you're applying 6 such filters, the size of the output would become, since it's 32 by 32 and 5 by 5, you get 28 by 28, but you get 6 because you're applying 6. Now, when you apply a filter of size 5 by 5, what happens is, on 28 by 28, if you apply 5 by 5, the output would be of size 24 by 24. And you're applying 10 such filters. So the size depth will be 10. Here, even if you don't give 6, automatically the 6 is taken. That's how it will prove this. And you know that in every hidden layer, hidden neuron, you'll have an activation function. And we're using ReLU activation function. When it comes to images, usually people use ReLU activation function. So here we are giving input as an image. That image will go through series of layers. Con layer in which ReLU activation function is used. Another convolution layer in which again ReLU activation function is used. Right? So on and so forth. These are nothing but neurons. Think about this as a hidden layer. Convolution layer is the name in CNN, but think about that as hidden layer. So you have convolution layer with ReLU, convolution layer with ReLU, then pool. What are these pooling layers is something that we are yet to talk. We will discuss. Then here also you have ReLU, conv ReLU, means convolutional layer in which you have ReLU activation function. Then pool, conv ReLU, pool. This is a standard combination which people give friends in neural networks. Conv ReLU, pool, conv ReLU, pool, conv ReLU. This is a standard thing that we give. And then you have the output layer, which is called as fully connected layer, or this is also called as multi-layered perceptron, artificial neural network, dense network, all mean the same. So within CNN, what happens is you'll have two layers, convolutional layers and dense layers. Convolutional layers will extract the features from images. Okay, from images, the features are extracted. Then on those features, you apply your multi-layered perceptron, and finally you get an output. This is how your convolution neural network works. Okay. Of course, there are quite a few things that we need to talk about, but then I will stop here, quickly do a recap, and then we'll proceed further. So friends, we are talking about machine learning, in which we are talking about supervised learning, neural network algorithms. In neural network algorithms, we are talking about convolution neural network. In convolution neural network, it can work on videos and images. And when it comes to layers, you'll have convolutional layers we discussed, and striding also we have discussed. We are yet to talk about pooling layers, padding, Vaishnav, etc. Tomorrow, when we connect, we shall talk about each one of that. And I would like to leave the rest of the class for questions. So attendance link is given, but then please ask me if you have any questions. Feel free, friends.